record to this. Okay, so I don't know কোনো একটা question করেছিলা and that was the transition point, meaning I was switching, so I didn't see that question, and it's not in the history of Zoom for some reason. Uh, uh, Not exactly. Fractional coordinates and Miller index are not same because Miller index they are integers, but fractional coordinates they range from 0 to 1. Okay, but the form is the same. With Miller index, you can go beyond the unit cell. With fractional coordinates, you always stay inside the unit cell. Okay, they're close, but not exactly the same thing. It's just like the convenience, like কখন কোনটা useful হবে. They'll, if one doesn't specify the nature of those coefficients, then they may look the same. Okay, I think I've started recording. Yes. So let me discuss the density of states. তারপরে I think I'll share a paper on density of states that you can read. Um, it's important to understand density of states because it can define the types of material properties at different energy levels, especially near the Fermi level. Like, is it a metal superconductor, or how many carriers are there? You can find all those informations from density of states. Um, um, Parabolic bands. Parabolic bands are the standard examples for, well, studying the density of states. So what are those? We know the energy, kinetic energy can be written like this. Let's say half mv squared, or p squared over twice m. And in quantum mechanics, p is h over h bar k. So h bar k whole squared over twice m. So E of k is h bar squared over twice m k squared. And this is the equation of a parabola, right? So that's why they are called parabolic bands.
Sir, are you sharing a screen? I cannot see one, unfortunately.
Okay, I think, thank you for reminding. I don't know. I forgot to share. Okay, I think I'm sharing now. Okay, yeah. Can you see my screen now?
Yes, sir.
Okay, so parabolic bands is just half mv squared, and we can also write it like p squared over twice m. P equals h bar k in quantum mechanics, and that's how we get this dispersion relation for parabolic bands. And if we plot this is nothing but just k squared, right? Multiplied by a constant. So that's why they're called parabolic bands. And what is the density of states, or DOS? Sometimes written like this, D small os. It's like, different notation. So DOS, or density of states, G of E, is defined as the number of available quantum states so number per unit volume per unit energy range. Okay, so G of E is dN over dE. Per unit energy range, that's why we have dE here. And it's the number, so we have the number here, change of number, or okay. And this N is number of available quantum states per unit volume, and energy range is dE. So that's the defining equation of G of E. Let's consider 3D case. Uh, we want a number of states with wave vector k or less. With wave vector k or less. Wave vector, so there could be a lot of different wave vectors, right? মানে তাদের ম্যাগনিটিউডটা ডিফারেন্ট হতে পারে। সো যে সমস্ত wave vector k that the magnitude is k or less, we consider only those wave vectors. If we how do we can actually draw this. So k is kx x hat plus ky y hat plus kz z hat, right? And we can draw a sphere like this. Okay. Okay. And let's say this is kx, ky, kz direction. Okay. And if we define a particular vector k like this is our k. Okay. So when I say number of states with a vector k or less, meaning if we take xyz coordinate of those k vector and draw a sphere with radius k, then any k vector with magnitude smaller than k will be inside this sphere, 3D sphere. It's like mathematical, this is a 2 sphere, but let's just call it 3D sphere for now because we're considering all the points inside the spheres as well. Uh, let's not go there why this is a 2 sphere. Simply any vector that's inside this sphere. Does it make sense? That's what I mean by the first sentence, number of states with a wave vector k or less. Okay, so n of k, number of states, will be, what's the volume of the sphere? 4 over 3 pi r cubed, right? Radius cubed. That's the volume. And
Yes, sir.
we have a constant in front, which is v over twice pi whole cubed. Let's just say this is a constant for now. We'll see how that constant comes in a bit. So we have n of k, and the formula says g of e is dn over dE, right? So dn over dE is equal to dn over dk over dE, because this is a function of k. Just a chain rule, okay? And what is dn over dk? V over twice pi whole cube is a constant. 4 over 3 pi, that's the another constant. K cube becomes 3k squared. And we have dk over dE. Now let's go back a little bit. And here we have dE over dk. We can compute du over dk from this formula. H bar over twice m will be twice k, right? So h bar over m is by square over m times k. So dk over de would be m over h bar squared 1 over k. Does it make sense? Let me copy from there and have it here on the side. So we write v over twice pi whole cubed 4 by 3 pi times 3k squared dk over de is m over h bar squared 1 over k. Okay, and then finally we have the expression v over twice pi whole cube, and you see these three cancel out each other, and um, we have the k and k squared, so that cancel out the k. So the expression would be something like 4 pi m over h bar squared, um, h bar squared k, I think. Uh, is that okay? Do you think I made a mistake? It's possible. I think I need to write that here as well. Okay. So this says k equals twice me over h bar squared square root, right? So we can write, write k there, and the final expression would be if we write twice, 2 times twice pi, and this twice pi whole cube, they make twice pi over v over twice pi whole squared, and if we plug that in, we'll have 2m over h bar squared 3/2 square root of e. Okay. Factors aside, does this square root of e make sense? That's the question. ফ্যাক্টরগুলি তোমরা চেক করবা যে is it correct or not. That's how we get g of e. Does it make sense, this factor? I mean, the square root of e?
Yes, sir.
Okay.
I think so.
Okay, good. This is for 3D system, meaning if you're, let me try to plot the graph. If this is of e of k, and this is k, and this is the parabolic band, then the density of states for this band, g of e as a function of e, would be square root of e. Like, I think square root of e is like this, right? For just one band. Is that the shape of square root of e? I keep forgetting. Uh, let's check. Yes, that's how it looks like. Okay. Now, what does it mean? It just it's just a graph. What does it mean? But it means a lot of things. Whenever you see g of e is going like this, square root of e means that corresponds to parabolic band. মানে complicated material অনেক সময় হয় কি there it's not a parabolic, it could be something complicated. So when things are complicated, um, it's like এখানে হতে পারে যে এর মধ্যে প্যারাবোলিক কন্ট্রিবিউশন আছে, লিনিয়ার কন্ট্রিবিউশন আছে, কিউবিক কন্ট্রিবিউশন, বিভিন্ন ধরনের কন্ট্রিবিউশন আছে। সো জি অফ ই যদি আমরা স্কোয়ার রুট ই এর মতো দেখতে পাই, দ্যাট মিনস ওই ওই পার্টটুকু প্যারাবোলিক ই থেকে এসেছে। Does make sense? মানে these are kind of additive. Parabolic, square root of e of density of state comes from the parabolic bands. That's the point. And then we also have 2D system. Um, again, E is h bar squared, k squared over twice m. It's always like that. And n of k for 2D system would have twice a over twice pi squared pi k squared. এটা এভাবে কেন লিখলাম? ফর এক্সাম্পল, প্রথমে যেটা লিখেছিলাম, this is the volume of the sphere, 4 by 3 pi r cubed, here k cubed. So we have v factor volume over twice pi whole cubed. In 2D, we have the area pi r squared, area of a circle. That's why we have area here, twice pi squared here. It's like kind of মনে রাখার একটা easy way. We'll see how these factors are there in a minute. But if this is n of k and that's the e for 2D case, and you compute g of e by dn over dk de, in the same way, you'd see, uh, the density of state would be a over twice pi m over h bar squared, and that's it. A constant, there is no e. Okay, meaning for 2D case, density of state is a constant for parabolic band. Okay, meaning this is important for 2D materials, for example. Meaning if you have a material where say conductance is along x and y but not along z, for those type of material, density of state would be a constant for parabolic bands. Okay, and for 1D case, E is h bar squared, k squared over twice m, and n of k would be just twice k, right? L over twice pi, here just k, right? Because pi r squared is the area, and when you are in 1D, you just have k length. This is a circle, so area is pi squared. This is just a length, so just the k here. And the density of state would be, if you compute the same way, it will be 1 over pi m over twice h bar squared e. In another word, it will be 1 over square root of e. So it diverges as e goes to 0. Okay, so in 1D case, density of state is 1 over square root of e. In 2D case, density of state is constant. In 3D case, density of state is square root of e for parabolic bands. If you have different kind of bands, density of state will be different. So if you have a few things in mind, like for parabolic band, these are the 3 cases. For a cubic band, for example, these are the 3 cases. Sometimes analysis becomes easier. Okay, and I'll share a paper that will discuss these, like how density of states is related to the bands, and when it's important, how it's important. Okay. So that will be your one assignment this week. Like, just read the papers. I think it's a 3-page paper. Just half an hour you can read it. Just try to mark the lines, important lines. Okay. It's kind of a general paper, meaning if you work in any field that kind of uses density of states, that paper could be important, right? It's like a general thing. Now, the question. Why do we have this factor v over twice pi n cube? Uh, okay. Okay. So why do we have that question? Now, if you remember, have a wave in a, okay, standing wave, right? I think we have seen standing wave, all of us, right? More or less.
Yes, sir.
So standing wave is, you have two boundary and the wave is kind of trapped here. Length is say, from 0 to L. That's the length of the um, boundary. And standing wave is a sine wave, then we write it as sine kx, right? Just a simple wave. I mean, খুবই simplified example দেওয়ার চেষ্টা করছি. For in 1D case, just a sine wave. And the sine wave must satisfy the boundary condition, meaning, let's say this is psi of x. Quantum mechanical symbol, don't get scared. Psi of 0 must be 0 and psi of L must be 0. কারণ হচ্ছে sine is the amplitude, right? So on either side of the wall or the boundary, sine wave must have 0 amplitude because it's fixed. It cannot physically move. And if we impose this psi of L equals 0 condition, we have sine KL equals 0. And question, when do we have sine equals 0? Sine 0 degree is 0. And sine pi over 2 on 90 degrees is 1. Sine 180 degrees is 0. That means this is just n pi, right? Sorry, not this. KL is n pi. Does it make sense? KL is n pi. Then we get the condition satisfied. So K is n pi over L. Okay. Question? No. All right. This is for 1D case. And what about 2D case? If the wave is, trapped in a 2D system, then psi of x comma y would be sine kxx plus kyy, or sine k vector dot x, or say r. And sine k dot r must be 0, right? And I think, oh no, wait a minute. For 2D case, we consider the wave to be we use separation of variable method. So the solution becomes this, kyy. Let's write it like this. That's easier. Okay. So in that case, this is easier way to explain. In that case, kxx or kxl must be n pi, and kyl must also be n pi, but let's call it, this is nx, this is ny. Okay, so the k vector would be kx x hat plus ky y hat, or nx x hat plus nx y hat times pi over L. Does it make sense? Like I'm just combining two coordinates together. Okay. In 3D case, it will be, pi over L is there, nx x hat plus ny y hat plus nz z hat. Okay, x, y, z. So here we have pi over L factor. in front. That's important. এখানে pi over L আছে. So if we want to measure length, then it will be just pi over L. If we want to do area, right, like this system, then pi over L times pi over L, that becomes pi squared over L squared, or pi squared over area. And if you want to do volume, pi over L whole cube, that will make it pi cube over volume, right? Uh, that's okay. We have this factor here. Now, um, this boundary condition 0 to L is one way of writing it. Another way of writing it is uh, marking the middle point as 0 and having the boundary minus to run from minus L by 2 to plus L by 2. If you have instead of L, if you have L by 2 there, everything remains the same except you have 2 here, twice L. Okay. And that, oh, no, I made a mistake. You have 2 there, twice pi over L. And that makes this twice pi whole squared. And this is twice pi whole cube. Okay. Because it's just choice of unit. So factor of 2 with pi is just how you choose your boundary condition. Okay, so now we have this factor pi 2 pi whole cube over v, 2 pi squared over a, and those are the exact factor we have in front, right? Because see, n is just a number. When you do k cube, in k we have twice pi over L, right? And some x comma y comma z. Some number, some number, some number. That's the k vector, right? So when you cube it, you have twice pi over L already there, but n is just a number. So we multiply by v over twice pi so that n is just a number. Does it somewhat make sense? That's if you choose your boundary condition so that k is pi over L, then this factor would be v over pi cubed. It depends on the convention. Does it somewhat make sense, like the factor? No one is saying yes. But you have to ask if you need me to explain a little bit. Am I think I'm connected. Okay. So that's density of states. And the paper I have, where's the paper? Let me uh, um, let me try to find the paper. Density of states. Where did I put that paper? Yeah, this is the paper. Okay, let me share my screen, the desktop screen. Leave meeting. We're almost done today. Can you see my screen?
Yes, sir.
Okay, so this paper, How to Analyze the Density of States by Michael Toriyama. This is an interesting paper. Uh, and Here it shows if the dispersion relation is k squared parabolic band, then the density of state is square root of E. If the dispersion is k linear in 3D, the density of state is E squared, and those are important. Okay, because you see, uh, and this is the energy gap between two bands. Let's say this is like a semiconductor. There's a gap. It depends on the gap actually. So depending on which type of curve it is, we see the density of state, and the gap is also visible in the density of state. And if we have multiple bands in the energy as a function of k, see, we have two parabolic bands, and density of state up to here is only for that band. And from here, we have both G1 and G2 for both the bands, they contribute. Okay, so and the gap is also there. Okay, that's how you can kind of relate which band or which part of the density of states is related to which energy band. And these are more complicated example. Just read it once and probably you'll have some ideas how things work. Okay. And when you see m star, that's just the effective mass, meaning remember the equation E equals h bar squared k squared over twice m. For arbitrary bands, we call that m star. We can compute it from the bands. Sometimes you'll see electrons have a little more, a little less mass than usual. That's because they have some kinetic energy with them. So the mass is a little different. It's not fundamental mass, just something to make the analysis easier. Okay, just read this paper once, you'll have some ideas. And I think I can share this paper in Discord. Okay, I'll share this paper in Discord. Or do you think it's easier if I share it in Google Drive?
Discord will be good, I think.
Okay, yeah, and yeah, that's it for today. But now I needed some help from you guys. So there is a program, 1Year90. Is useful when you want to build the Hamiltonian from the computation of a quantum espresso. And I'm actually stuck somewhere. The program is not, for some reason, not working. So here I have the STF file. It's just a regular STF file, but the grid is 444. Okay. And I also have NSTF file. The grid is again 444. Just standard files. And if I go there, maybe I can increase the font size. And then Hamiltonian. Yeah, I have these files here. And if I can run STF computation, MPI run, NP, PW, NP1, PW.x, input STF.input .output. It's completely fine, it works. And if I do NSTF, that also works. Just takes a little longer time, but it works. And then what I need to run this si.win file. This is the input file for 1Year90x command. The way to run it is -pp is the pre-processing of some steps. and just the input file. And so let me talk about this input file a little bit. So now you provide number of bands and number of iterations and the unit cells, and some projections that's important there, um, and disentanglement. But these are not the problems. These are okay. The problem is specifying the grid. So for our SCF file, I have 444, and NSCF I have 444, and 4 cube is 16 times 4. What is that? 16 times 4, 40, 64, right? So if I go to nscf.out file, I see there's a line. It says number of K points 64, right? So I have 64 K points, 0, 0, 0, 0.25, minus 0.25, 0.25, 0.25, so up to 64 in different coordinates. And there's a command, I think this command that I can run. And yeah, this is, let's do 65. If I run this command, it will generate a file, and this file contains all those 64 points. You can match with nscf.out, right? All these points, 64 points is here. And I can copy it from there, go to silicon.win. No, not this one. Si.win. I tried many things. So just 64 points, and this should be 4, 4, 4. So it knows there are 64 points. This command is a little complicated, but I think I have listed this command in the overlay file. So let me compile it again. I had somewhat listed, not everything, but basically this awk command, I can copy this last command and okay. I have both commands here, right? So what it does, it reads number of K points text from the NSCF out file, first 217 lines, and then it just takes this, it runs this tail command to, I think, skips those last two lines. I forgot what it does. Like while using it, I build the command and then I forgot. But then this awk command will skip the first line and then reads column 5, 6, and 7. Those are basically the K points, and you have the K points. You can direct the output to the kpts.dat file, and you have the K point. So explore that command a little bit. You will know how it works. So I have the K points there. That's fine. The problem is if I run this command, pre-processing command, it says something is wrong. And if I go there, this is the output file that generated by the 1year90x command. It says kmesh something wrong, found too many nearest neighbors. Okay, so what I tried deleting everything and just 1, 1, 1, just a single point. Then it works and doesn't give any error. Okay, writing si.nnkp, which is this file. And I need this file for further computation for all those K points. Um, uh, প্রবলেমটা কি একটু বুঝতে পেরেছো আসলে কি কি দরকার মানে স্টেপগুলি?
জি স্যার, বুঝতে পেরেছি।
Now, if you can kind of dig a little bit, you can try to install One-Year to your system, local system, try to explore how it works. Just SCF, NSCF computation, then you write this si.win file and try to run it for all the K points. You can change the mesh if needed, but I need this si.nnkp, and that's important to get the Hamiltonian. I think I'm just stuck there for some reason. It is not working. And it's taking a little longer to figure out why. So I thought, okay, maybe you guys can explore as well and see if you can find a solution. The official website for this One-Year function is here, oneyear.org. It's called maximally localized One-Year functions. And it can be used to compute the electronic properties. Yeah, so you can maybe explore in this direction a little bit. And if you find something, hopefully that will help the entire group and myself. Any questions? Okay, you can actually so have you used a PWTK scripts to run the computation? If you haven't, try that. It can simplify a lot of the workflow kind of entirely. And so ultimately what we'll have, we'll do some parameter optimization, and we'll have a single PWTK script. If we run that script, that will generate the Hamiltonian for us. Okay, like this One-Year command, it can also be implemented in that script. So when you run that script, that will run the One-Year computation as well. But I need to configure it properly. It's not working so far, and I need help from you guys. Any questions? Okay, so that's it for today. Hopefully in the next class, we'll try, I mean, to show you the topological behavior. I need to discuss those models, and hopefully we'll start next week. And you see, your assignment for this week is to, the main assignment is to be comfortable with running these SCF and SCF computation, getting the bands and getting the density of states, plotting them using Nuplot or Python, also how to use PWTK. And when you are comfortable there, right, then probably we can proceed with those computation of those different materials and try to see their properties. So yeah, hopefully, let's see how far we can go. But I need you to kind of invest a little more time and also contribute to that overleaf document. Okay, and just read those section. If you see there's things can be improved, text me, or if if you want to contribute, you can also write there your like organize things a little differently, proofread the document, and maybe give some new ideas like how things can be organized. Okay. So in the research, you are you're not a student, you're also a researcher. So take ownership of the part that you are doing. Okay. All right. So that's it for today. If you don't have any questions, I guess that'll be all. Yeah. See you next week.
Thank you, sir.
You're welcome.
Assalamu alaikum.
Walaikum assalam.